Hello everyone, welcome back to our episode 15 of the number series. For today's video, we'll be talking about decimals, especially the period length of a specific fraction expression. And let's begin. So first we need to find the period of expression or of expansions of those fractions. Well, we know that according to this formula over here, so the period of a specific fraction is determined by the smallest r, such as 10 to the power of r is congruent to 1. It's equivalent to finding the order of 10. So still, like, based on what did we learn when we are finding the orders, we only consider those divisor of 5 modulo, the modulo number, and we know that it cannot get any greater than this number. So and we just try out those values and see if they're congruent to 1, and we find the corresponding value of r. Okay, it should not be too hard, just like what did we do in chapter 10. Okay, and these are the answer. And question 3, we're gonna find the smallest r, such as 10 to the power of r is congruent to 1 modulo m. It's just like what we did, so just check your work. First one should be equal to 2, and the second one should be equal to 3. And the 4, find the smallest positive integer r, such as 10 to the power of r congruent to 1 modulo n if n is 42 or 45. Well, this is impossible because we know that the order doesn't exist when the modulo and the remainder, they share kind of and the number, they share some kind of factor other than 1. We know that's not true, so there's no solution. And okay, I accidentally put the question 8 over here, my bad. So we're gonna continue to question 5. So prove that if the decimal expansion of 1/n in the base b, that's it, if and 1/n equals to d1 over db, blah 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 blah. Okay, so we know that this is what we get, and we know that it terminates to some kind of digit, and we can rearrange this equation, and we got this. And n has to be a divisor of b, therefore all of its prime factors should be also a divisor of b. Okay, Okay, so question 6. Let me move the camera by a little here. Okay. Question 6. Prove that if every prime factor divisor of n is a divisor of b, then decimal expansion of 1/n in the base terminates. Well, it's kind of doing this backwards like the last question. And we rearrange it, and we take b to the power of m, where m is the maximum power among those exponent, and we call this to be a terminate expression. And since this is in base b, this is definitely going to be it's going to be a limited amount of digit. It's just going to push this to towards right by m different places. And question 7, which of the reciprocal of those they have the terminating decimal expression in base 12? Well, we according to our theory of the question 6, every single prime factor of those numbers, it has to be a divisor of 12. And we check only those 3 numbers satisfy the condition, and only their reciprocal is terminates. And question 8, prove that if n and b, they don't share any factor, then the period of decimal expansion of 1/n in base b is the smallest positive integer such as b to the power of r congruent to 1 modulo n. And it's just kind of similar like what he did here. We're just going to replace 10 to b, that's it. And we're gonna prove that there's at most r digits, and also there's at least r digits, and therefore it has to be exactly r digit. And that's how we get the answer. And question, well, this is the process here. Well, it's just very similar. If you don't get it, you can just take a look at the example that the book gives you. Just replace 10, every single 10 with b, and you should be getting the same result. And question 9. In base 2, what is the period of decimal expansion of those fractions? So if you want to calculate the decimal expansion exactly, we're gonna use our division algorithm here. And like here, we raise it by the power of 2 instead of 10 now. And then we find the largest number for which, sorry, hold on a second. What's going on here? Okay, so for example, we are taking 1/9 as an example, and we're gonna find the maximum coefficient that's multiple of 9 but smaller than this number. We take the remainder and pass it on, and we take those numbers, and we have the number here. Okay, it's kind of like what we did last chapter. We use our division algorithm. So I'm not going to speak about that for too long, and I'm just going to move on with the question. So question 12. Okay, finding the decimal expansion. Well, this is just in another base. The process is still the same, except those numbers could be any number between 0 to 11. Okay. And question 13. Okay, it's just calculation. The first 3 questions, you're gonna find it has form like this, and this is the and this is going to be your induction assumption, and this is going to be the base. And we're gonna find that unless k equals to b minus 1, it's always going to give you the next expression of k plus 1, and the induction is true. If it is b minus 1, it's just going to reset to 1. Okay, that's what you're gonna find. And question 14 shows that this is irrational. Well, it is some kind of rational number. It either terminates or it has some sort of period. But in base 7, and this is clearly not a case, we can see that it's going to have, like, for each 7, it's going to have more and more zeros in between 2 7s. So there's no period exists, so this is irrational. And question 15, this is interesting. So the answer is a yes, because there's no maximum to the sequence where, like, how large it could be. And we know that this diverges according to the integration test of the Maclaurin series. And it is not always unique to express a certain fraction. For example, 1/2, it could be expressed directly by 1/2. It could also be indirectly expressing as 1 over 3 plus 1 over 6 equals to 1 over 2. Like this. Well, this 120, this is actually a number of the digit. It's not separate digits, okay? Just not mistaken this. And that concludes our section for today. And it's a little short, but because it's a lot of questions, just it's calculation based, and there's not a lot to explain. And thank you for watching. See you in the next video. Bye.